And all the reviews say, don't be a white guy with dreads. Okay, so that's like, that is, like, almost everyone agrees that that's a bad idea. So, I don't know. I think dreads are really cool, but apparently it's not a good thing. So, yeah. So, Chapter 3, Transient Response Performance. Let's review just for a moment what we're doing here. So we're going through the 3 different performance criteria, or performance categories, really, for control systems. So before we start designing them, we have to know what kind of performance we'd like out of them and how we're going to characterize that performance. So we started with stability in Chapter 2, and that was pretty straightforward. I mean, there's a very clear line between stable and unstable, and then there was the marginal stability definition. All pretty clear stuff. And you usually just want to make sure your system is stable. There is an amount of stability, a sort of robustness that we discussed too a little bit, but so you could be like just barely stable, and that's like a bit concerning. But there's a pretty clear dividing line between stable and unstable and all that. So we learned about that. We learned about how to go ahead and compute, like, is this going to be stable? For what range of gains is this going to be stable? That type of thing. And then now we're going to turn our attention to transient response performance for Chapter 3, and then we'll move on to steady state performance in Chapter 4. So stable system time responses are often described in terms of 2 intervals, loosely defined as transient, the first part, during which the effects of initial conditions and I would add step or impulse inputs remain significant, and steady state, the second part, during which the response has settled near its final value or final amplitude of oscillation. In this chapter, we consider performance in terms of the transient response. In the next, we will consider it in terms of the steady state response, specifically as steady state error. The transient response characteristics are typically found via 2 methods. Analytically, and there are 2 subcategories of analytical characteristics of transient responses. So precise analytical for first and second order systems without zeros. So if we have first and second order systems without zeros, we're going to actually derive several analytic expressions in a future lecture, lecture 3 too. And 1b, approximate analytical, for first and second order systems with zeros and higher order systems that have dominant poles relatively close to the imaginary complex plane axis. Those are the 2 analytical ways we'll evaluate performance. We'll develop performance criteria. It turns out that this method here is very powerful for doing design, even if we don't have a precise analytical expression for a given system. So if it's a second order system with zeros, for instance, or if it's a higher order system, we won't have an analytic derivation necessarily for the performance criteria. However, we'll still use this sort of second order approximation as a starting point for design. Even though the approximation might not be great, it gives us at least a place from which we can start bootstrapping our design. We can start iterating from there. So that's the idea with that, and we'll talk about that more extensively. And the other broad way of evaluating performance criteria is to numerically simulate the response. Okay, so that's another method. Simulation has some drawbacks, though, especially for design, because you can only simulate something with concrete numbers in it, so you have to essentially guess and check if you're going to use simulation. So it's not a great design tool by itself, because if you're just going to guess and check your way to a solution, oftentimes your parameter space is very large. Imagine you have 3 parameters that you can vary continuously. You have a whole lot of space to vary each one and do a full search of the space. So it's very good to have more than just numerical simulation, which is why we still, even though analytically we can't do things always precisely, we still use the approximation to give us a starting point from which we can optimize. Okay, we'll talk more about that. The analytical method is especially advantageous for design. Design methods we will learn in chapter 6 of these notes require we place the closed loopholes in the complex plane. The transient response depends very much on this placement, and exactly how is something we can better understand from studying first and second order system response. Okay, so we're working our way toward doing this design, and understanding first and second order response really extensively is going to help us when we make those design decisions. We can only simulate systems defined by concrete numbers, so simulation, although powerful, is typically more helpful to fine-tune a controller rather than design it from scratch. So if you just start out a search for an optimal or a good controller design, and you have no starting point, you could search for a long time before you find a good spot. If you give it a good starting point, which is what our approximate analytical methods will do, then using simulation to fine-tune is great, is a really good tool. So there's a sort of balance that we need. And in fact, so we're going to use simulation pretty extensively. We're going to use MATLAB tools in a lot of the remaining content in this course. And I'm going to try to get our final exam to be scheduled in the computer lab, so we'll have access to MATLAB for the final exam. We can do everything by hand, but it's just pretty tedious, and I think that you guys learning the tools, the MATLAB tools, is actually kind of important in this last bit. So we'll talk about those tools extensively, and you'll use them in your homework. There are some methods to do some of this work by hand, but it's kind of tedious, and it's not necessarily that enlightening to do it by hand. So that's why I'm leaning towards using MATLAB, and we'll see more about how that works later. So you guys will be able to design a controller with MATLAB on the final, hopefully. This is how we're going to do it. It's going to be super fun. All right, any questions?